Hello and welcome to this network education video. My name is Russell D. Long and this is the Sctp protocol overview. Sctp, or Stream Control Transmission Protocol, is a connection-oriented transport layer protocol very similar in operation to TCP, or Transmission Control Protocol. Directly based off it, as a matter of fact. Now you might be wondering, looking at this intro, why I'm going over a transport layer protocol when we're talking about the EPC, when we're talking about really application layer signaling protocols from the perspective of the OSI model. Well, the reason is Sctp is a very different transport protocol, and it's very prevalent actually in the EPC. Sctp was designed to provide layer 4 level redundancy and high availability for those signaling protocols that we're going to be using in the Evolve packet core. It's also very prevalent in telecommunications in general, particularly if you're looking at SIGTRAN or SS7 over IP and message transfer part over IP. It's a very popular transport layer protocol to use, and there are some intricacies with it, and particularly its use of paths, which we're going to talk about in a little bit, which make it a little bit more complicated and something you really need to think about compared to TCP. So, protocol overview. Sctp was designed in defined first in RFC 2960. It is a connection-oriented transport protocol built to overcome specific problems that the telecommunications industry had with TCP. It uses sequence numbers and acknowledgement numbers to provide delivery guarantees, and a lot of these are exactly the same as TCP. Uses a receive window between peers to indicate what amount of data can be received in buffer. This is all pretty much directly TCP terminology, and it is the dominant transport protocol for many telecom applications and standards. It is not nearly as common in enterprise environments. So if you're not familiar with TCP already and some of these terms are new to you, this is just sort of a very simple illustration of normal message exchanges that will be happening between two endpoints. So A, let's say, is a client, B, let's say, is a server. Actually, no, sorry, reverse that. A is a server that's sending data to B, which is the client, so he's sending data message number 100, sending data in message number 101, and then B sends an acknowledgement saying, I acknowledge all the way up to data message number 101. So that's this bit here when I say uses sequence numbers and acknowledgement numbers to provide delivery guarantees. So he's saying I'm sending 100, 101, and you make sure that the other side confirms receipt of those messages for a guaranteed delivery. Receive window, that just refers to how much information a system can handle at any given time. So if B had a low receive window, A wouldn't just spam it with data that it's not able to deal with before B acknowledges and releases traffic from its buffer. And again, dominant transport layer protocol for telecommunications. We just talked about that as well. So, how Sctp kind of works, the association is really, you could map to TCP terminology and say that that is like a TCP session. It is formed between two endpoints. Now the difference between TCP and Sctp, the biggest difference is probably standing out right now, that you can have multiple IP addresses. And this is kind of the game changer. You have multiple IP addresses between systems with the same session. So endpoint A, endpoint B, this is one Sctp association or one transport layer session with one or more IP addresses on both sides. In fact, one of these could be IPv4, another one could be IPv6. So different IP addresses where you've got different paths, these four lines here where you see arrows. You can have keep alive messages being sent from 1111 to 3333, keep alive from 1111 to 4444. All four of these paths being maintained through keep alive mechanisms independent of each other, all part of one association between endpoint A and endpoint B. So Sctp terminology. A chunk is an individual Sctp message sent within a packet. You can have one or more chunks in a given packet. A data chunk, or chunk type 0, is really the most common and most normal Sctp chunk type, and that is a data chunk, like a TCP data segment. So in TCP, where you send data segments, in Sctp it sends it as part of the message in a chunk called a data chunk where you then have the actual chunk header, and then you have the actual data being sent to the upper layers in the OSI model. You have a path, what I just mentioned. A path is a connection between two endpoints. So again, back to this association, this one arrow, or let's say this one arrow between 1111 and 3333, that is a path. An association, like a TCP session, is the overall connection between two endpoints. TSN here is a difference between TCP. TSN is transmission sequence number, roughly the equivalent to TCP sequence number, but these increment quite differently from TCP. So where TCP, you start with a randomly selected sequence number, and then you increment based on the number of bytes of data that have been sent and received. Well, this TSN mechanism, you do similarly, where you take a random TSN number, a transmission sequence number, a random starting point, but then you increment based on the number of chunks received. So if you've received 3 data chunks, no matter how many bytes they contain, you'll be incrementing the transmission sequence number by 3. Heartbeats, these are roughly the equivalent to TCP keep-alives, one difference being that these are their own chunk type. And you'll see often where TCP dealt with conveying information through the use of flags, Sctp uses explicit message types, where it can give more granular information such as error codes or provide context behind why a particular chunk was sent or received. Shutdown, roughly equivalent to a FIN flag in TCP. So what this does, and these two are sometimes misunderstood, a FIN does not technically end an association. A FIN flag in TCP says that the side that is sending the FIN has finished sending data. Potentially it could keep receiving data. It doesn't actually end the TCP session. In the same way, shutdown, the shutdown chunk in Sctp, is considered to be a graceful disconnect between the two peers. So if you send a shutdown, you're saying you're finished sending data, not necessarily that you aren't able to receive data. And an abort, equivalent to RST flag in TCP. So an abort is the opposite. Abort is closing the door on the other side, saying this session is over. Or in Sctp terminology, this association is over. So session setup, the 4-way handshake. Starting with an init, by the way, this is different than TCP, which uses a 3-way handshake, where you see SYN, SYN-ACK, and ACK, so you're just exchanging initial sequence numbers for the session. In this case, we have a 4-way handshake, where you have an init sent by client, includes its verification tag, so you have an exchange of verification tags, and then the response to the init is the init ACK. It also includes what's called a state cookie. Now, I don't want to get into the details of what a state cookie is, but basically the way that this works with state cookie exchanges and cookie echo, where that state cookie is returned, it's set up in such a way that the server, that is the system that received that initial init, he does not keep any state information about this session that's being built until it receives the cookie echo and sends the cookie acknowledgement. It's intended to prevent one of the bigger limitations of TCP, which is its vulnerability to SYN flooding. That is, if a malicious system sends a large number of initial TCP session setup messages called SYN messages, you can end up filling up the state table of the receiving system. So if A sends like a million initial session setup packets to B, B would receive those SYN message, send a SYN and an acknowledgement, and wait and keep a record in its state table that it is trying to create a new TCP session. And if you build up 1,000 of those, it could be trying to wait for the setup of 1,000 TCP sessions, and eventually it's got no room or no resources left for new legitimate sessions to be created. Well, Sctp gets around this problem by having this initial setup messaging not require that the server keep any state information. So you have to actually complete the full handshake, the full 4-way handshake, in order to have any actual state maintained on the server. So it makes it more difficult for a system to try to perform a denial of service attack against the system that's running Sctp as opposed to TCP. Retransmissions. So if a receiver notices path loss And most of this is almost exactly the same as TCP. Again, I sort of sound like a broken record saying this is like TCP and this is like TCP. It's because really it pretty much is TCP, where they took that as a base and said, well, how do we build this so that it can support multiple paths? That's really what this is. So if a receiver notices path loss, it sends a selective acknowledgement indicating the missing TSNs, those missing sequences, those missing data chunk numbers. And it sends them 3 times to trigger a retransmission known as a fast retransmission. So, and then to the second point, really, they're almost the same thing. So if RTO is a timer, retransmit timeout expires without acknowledgements, retransmission is triggered. So if A, the way these two sort of operate, A sends something to B, he has this RTO timer that he's keeping track of and saying, I'm waiting for an acknowledgement for this because I sent this data chunk with TSN 25. I'm waiting for him to acknowledge 25 or send a cumulative acknowledgement of something greater than 25 without saying he hasn't received 25. So I'm waiting for 25 to be acknowledged. If that waiting time expires, this RTO expires, he's going to resend it. Again, the point of this transport protocol is to provide, or one of the points is to provide guaranteed delivery. So if something gets missed, it can detect it and send it again. The other part of it is on B. Sorry. If he receives, let's say this is 25, and he acknowledges it, and then he receives 27. His question is what happened to 26. So he can acknowledge 27 and explicitly say what he hasn't received, and he can send duplicate acknowledgements or duplicate acts 3 times indicating the TSN that he has not received. Selective ACK is where he says what he has received as opposed to what he hasn't, where he actually sort of cherry picks and says I have this, but I didn't get this. That's what a selective acknowledgement is. He's selectively acknowledging some segments without acknowledging all of them, or some TSNs rather without acknowledging all of them. So he can resend that 3 times to say, hey, retransmit. So you might wonder why he has this mechanism when this mechanism is already in place. Well, that's why it's called fast retransmission. So if B notices before A notices, before this RTO timer expires, he can use this fast retransmission mechanism to have A side send that number 26 that was presumably missing faster than this RTO timer expiring. So the connection ends up getting the information exchanged more quickly this way. That's why it's called fast retransmission. And forward TSN is a chunk type, can be used to stop this retransmission logic. So basically, if A sends, let's say 25, and in this scenario here where B notices, hey, I didn't get 26, if he's trying to trigger a retransmission by A, let's say somehow, by some glitch or some bug, A doesn't have 26 anymore. He doesn't have that information. He knows presumably he must have sent it at some point. Well, forward TSN is built into the Sctp protocol stack, and it allows the server here, this A side, to say, you know what, even though I didn't send you 26, I've decided it's not important. So just forget that I sent 26. I acknowledge that you didn't get it. You're telling me you didn't get it. I hear you, but it's not important. We can keep going. So I'm going to send you 28 next, and don't bother trying to get retransmissions for 26. It's not going to happen. That's what forward TSN allows you to do. Now, I mean, technically, just like with TCP, the expectation of a system that's sending a data segment, or in this case a TSN, is for it to duplicate that data and keep it in a buffer until it gets acknowledged that it's able to resend it. There shouldn't really be a reason why you can't resend it. The only really reason I can think of is if this was some kind of a real-time protocol where it doesn't make sense to retransmit. Although in that case, I'd wonder why you're running it under Sctp. But in any case, it has this procedure built in to the specs where it is allowed. Forward TSN, by the way, was added after 2960. It is not part of the original spec, so both sides would have to support that. So advantages of over TCP. Touched on a few of these already. 4-way handshake protects from SYN floods. It supports multiple IP addresses on both sides of a session. Protocol is not bound to one stream or even one IP version. It can even change these numbers dynamically over the life of the association. You could actually change 1111 in this case to 5555 through an ASConf, so a configuration change request message to B. It supports explicit error codes and message types. Selective acts are supported in all SCTP connections. So I put this explicit error codes and message types just because in TCP there are some cases where you kind of have to put one packet in the context of the rest of the session to figure out what it's really trying to mean. TCP keep alive being a great example. There's no like message type or something saying, "Hey, I'm a keep alive," whereas in SCTP there actually is, like it's an actual message type. So with only one packet, only with the context of that packet, that SCTP chunk type is heartbeat or heartbeat acknowledgement. So it's very clear and verbose that I am a heartbeat message between A and B. That is the reason why this message is being sent. It's very explicit within the context of a single packet, making it a little bit easier to work with in your troubleshooting. Selective acknowledgements are supported in all SCTP connections. In TCP, you kind of have the issue of different operating systems and different systems in general having different TCP stacks, where some might support selective acknowledgements and others might not. It's not required. It's actually negotiated in TCP during the handshake process, that SYN-SYN-ACK messaging. Whereas with SCTP, it's built into RFC 2960. An SCTP speaker, if you support SCTP protocol, you have to support selective acknowledgements. It's part of the protocol. Window size is 32 bits. This isn't so much an advantage of the protocol, but it does make it easier for troubleshooting. Similar to that selective ACK negotiation, window size is something that can be misunderstood. It is actually negotiated, or at least part of it is, in the TCP handshake. That is the window scaling factor. So this scaling window, in TCP, you have an advertisement. In TCP, you have this advertisement of a window scale factor negotiated in the initial SYN-SYN-ACK messaging in these options fields, where the TCP sender is saying, I support a window size of a 16-bit value, so 65535, 65,535, and by the way, multiply that window by 8. The reason for that is because the window size field was fairly small, 16 bits. Whereas in SCTP, they said, well, let's just make it a 32-bit value. Let's get rid of this whole scale. I should have said scale factor there, but it's the actual name here, not scaling window. So a scale factor, where I will multiply whatever I actually receive in this 16-bit field by this other field that I negotiate only once. So if you've captured a trace of SCTP and you don't have the initial handshake, you can calculate the window size. Whereas in TCP, even Wireshark could not tell you what the window size of a TCP session is if you did not capture that initial handshake. You could heuristically guess as to what the window size might be based on the behavior of the two systems as to what they probably saw as the window size, but you can't actually see it on the wire unless you saw it in the initial messaging. Whereas in SCTP, any selective acknowledgement will give it to you. So supports partially reliable delivery options. I mentioned that forward TSN. And it supports multiple IPs for multiple, even subnets, giving potential for layer 4 convergence to happen before layer 3. And I kind of drew this scenario here. Actually, I'll redraw this to clarify it a little bit for us here. Sorry. So here you've got an IP infrastructure. So pair routers serving. Let's say these are two servers. Let's say. Server A, Server B talking to each other with an SCTP association. These are SCTP endpoint A and endpoint B. They're talking over an existing IP infrastructure over a WAN. So let's say, let's use what I did before, let's use pink. So A might talk to B over this path here. Let's say they're going from 1111 to 3333. So you've got 4 paths, but usually you'd have a primary path as opposed to having all of them active at the same time. So let's say that's your primary path, 1 through 3. So this IP router going to this IP router, let's call them router 1, router 2. That's your main path. Let's say that this path had a failure right here. So the connection between router 2 and the WAN went down. Well, you've got different convergence elements happening at the same time here. You've got your layer 3 convergence. Your routing architecture will have to converge. What, from the perspective of router 1, what is the best path, the best IP path, to reach the IP address 3333? Well, he's going to eventually have to converge this way. Actually, yeah, let's go back to red. He's going to have to go this way, and this way, right? Well, in order for him to do that, that's based on what your routing protocol is. So if this is a WAN, let's say this is an MPLS VPN, a large one with a large service provider, and let's say you're running BGP between these routers and your WAN provider. Well, BGP typically takes a fair amount of time to converge, depending, like if this is a worst case scenario, this could be minutes to recover from this failure here. Whereas with Sctp, as soon as it detects this failure, if you've got Sctp keep-alives that are fairly aggressive, you could potentially notice this failure in sub-second, and within a second, your logic at a transport layer could say, I'm going to stop using this IP address, I'm going to stop using this IP address, I'm going to start sending, I'll make this thicker, I'm not sure how this is coming out here, I'm going to start using my secondary path through here. Right, so if the IP infrastructure was active, like let's say this is equal cost load balancing between these two routers and these two routers, where anything that came into this router 1 got routed out this way, anything that came into this router 3 got routed out this way, equal cost load balancing across the WAN, let's say did the same thing on the other side. No routing convergence has to happen in order for Sctp to make the decision that it's going to use a different IP address towards a different IP address. And the ability to target different subnets at a transport layer for the same association to keep that same session up brings a level of redundancy that isn't really available with TCP. Now, yes, there's different ways of achieving high availability with the same IP address. There's load balancers. There's anycast IP addressing. There's a bunch of things you could potentially do to virtualize an IP address and make it highly available across two paths. But this ability at the transport layer to inherently change the source and destination IP address based on an upstream link failure detection is something that TCP cannot do. And this is really one of the main drivers for why Sctp was built, this ability to have this high availability at a network layer across multiple paths. So possible problems with Sctp. First of all, NAT can create a conflict between IP information that's being exchanged in layer 3 and layer 4. So the way that these paths, just to quickly go back here, the way that these paths and this association is being built is at an Sctp level, IP addresses are being communicated between these endpoints. Use IP address 1111 and 2222. In fact, even upper layer protocols, Sctp calls it ULPs, upper layer protocols, can pass IP address information to Sctp to start using for paths. Diameter capability exchange request and answer messages include IP address information, which can be used by Sctp to decide what paths to create. So you have upper layer protocols conveying IP address information. Anytime you have that, you have a risk of creating problems if you're running it over a network address translation environment. That is, if you have an upstream router or IP device that is changing the destination or source IP address in an exchange between two Sctp endpoints, here you don't have a conflict, but you could potentially have an issue where this is a copy snapshot from Wireshark. This IP address in the IP header, this layer 3 header, might be changed. It's 192.168.0.101. Let's say this was going over the internet or something where it had to become a public IP. That had to become a public IP. A network address translation device is most likely not going to change the Sctp layer or even deeper down the application layer information that's conveying what the IP address is to use. So potentially you could run into problems when you're trying to run NAT with Sctp. Next, firewalls that support rules based on layer 4 information would have to support this, because you have to realize this is not just a different port number for a firewall. This is a whole different layer 4 protocol. Firewalls will typically support UDP and TCP. Those are much older protocols and much more prevalent. Sctp is its own transport layer protocol. So if you're going to have rules written based on Sctp port numbers, you would have to support Sctp in that firewall's logic. That is, when he sees the IP header and he sees the next upcoming protocol layer, and he sees I believe it's 132 for Sctp, he would have to know how to read that Sctp header to figure out where those port numbers are and what they are. It's pretty straightforward. Same deal as TCP. Actually, the ports are directly afterwards. Same deal as UDP, rather. Ports are directly afterwards, but basically the firewall has to support Sctp. Layer 4 deciding where data is sent and received reduces path predictability for network administrators. Okay. This is kind of cool. So there's really two scenarios that I see that could potentially be problems for people. I'll get rid of this 0 here just to demonstrate something. So let's say these are two different areas. Let's say these are two different sites. This could be two different states or countries or provinces where A and B are. And here you have this IP infrastructure. Typically servers and infrastructure or a big corporation will be serviced by two different groups. So you have kind of the IP infrastructure group who are thinking layer 1 through 3, and then you have the application group. And in really this case, the layer 4 and upwards group. So whether your primary path is between 1111 and 3333, as we discussed, is going to be based on A and B's configuration. Typically, the client would decide what IP addresses, or what your primary path is going to be. So that's going to be dictated at that layer, what your actual destination is. But if you're the IP person responsible for this middle box here, if you were to ask them, well, between your let's say country 1 and country 2, or state 1, state 2, your two main offices, where's traffic going? Well, they'd look at this architecture most likely and say, well, yeah, our primary path is going to be between 1 and 2 is going to be over this top link here, because I got a cost of 1. Well, if at an SCTP layer, all of your traffic, your main path is between 2222 and 4444, this is what your path is actually going to be, regardless of what the cost might say. And then, on the other side, if they did something like this to really force, these are route metrics I'm drawing here, sorry, so let's say this is OSPF just for simplicity. So lowest cost wins, let's say this is a single area, lowest cost wins. So in this case, traffic from A to B, even if it's 2222 to 4444, and let's just change thickness again here. In this case, the traffic would go like this. That might be your primary path. The other part of it is all of your paths would really, there's going to be a lot of redrawing, but it's to illustrate a point here. And when did I not draw? Oh, I didn't draw this one. Yeah, all of your paths are really going through the same pipe. So if you're the application person, you're looking at your configuration, you're saying, oh, I'm highly available, I have 4 paths. 1111 to 3333, 222 to 4444. I'm sending different keep alives on these different paths, so I'm fully available. What happens if this link, I drew this in red, so I'll draw a blue X. Sorry. I'll draw a blue X here. What happens if this fails? You lose all your paths. And let's say this is part of a larger architecture and you're subject to that BGP convergence that I said before, and let's say that's a minute. Well, then you've got all 4 of your paths down for a minute. If this is for some kind of a signaling protocol, let's say this is part of the EPS attach procedure. I'm not sure what order you're watching these videos in. This is part of the EPS attach procedure. Well, that procedure between the device sending an attach request and the attach accept, that's a 15-second timer in the phone. So if you're taking a minute to converge, well, that's already a fairly long time, but taking a minute to converge, you could actually drop calls or prevent new attaches from succeeding because of this convergence time. Even though it's just signaling, and even though signaling real-time requirements are not usually as strict as the actual voice payload or the actual payload of real-time applications, this could actually affect user experience. Yeah, so I guess just from those two elements, there is a newfound, or I should say with SCTP, Layer 4 based destination and source IP address mappings, there's a newfound need for collaboration and overall redundancy planning between layers 3 and 4, which very likely is going to mean between different operational personnel within this system. This could be 2 different companies, this could be 2 different departments within the company, but a lot more overall end-to-end planning is required for this kind of a protocol as opposed to TCP. It's much less predictable, and it's based on both the configuration of these systems, these end systems, as well as the IP infrastructure that they are carrying, or are carrying them rather. Last problem. Multiple data chunks in single IP packet are very common. This means that TSN numbers and acknowledgements can be harder to follow per packet than TCP streams. Very true. If you work a lot with TCP troubleshooting in Wireshark, especially if you're in the enterprise world, I hope that you do work with TCP troubleshooting in Wireshark a lot. Usually people will have profiles just for TCP where they set columns for TCP acknowledgement and sequence numbers so they can quickly do the math and see how things are adding up. With SCTP, you often find 3, 4, 5, 6 different data chunks being sent in the same IP message. So when you have that many data chunks, you have a whole bunch of TSNs, transmission sequence numbers, in the same message, and then you've got acknowledgements again with multiple numbers being referenced. And anytime in Wireshark where you have the same attribute or the same container occurring multiple times in the same packet with different values, where they can occur one or more times with or without duplication, it can be very difficult to write a column rule, even if you're going with occurrences, to actually map out everything as cleanly as you can in TCP. I would say it's much more difficult. It's a bigger problem with other signaling protocols, especially in the telephone SS7 over IP space. But it is a problem here, and I'll go over it when we go over actual Wireshark traces in just a moment. So I'm going to be ending this video right about now, and what's going to follow, either as part of this video or as a separate video, I'm going to be making a Wireshark specific video where I just go over a couple example packet traces of SCTP and just go over some of the tools that Wireshark has specifically for SCTP. Just like it has specific diagram and flowchart and graphing tools for TCP. It is very similar for SCTP. So thank you very much and for watching. I hope this was of value to you, and please proceed to the next video. Thank you.